In this recording, we're going to look at tree diagrams and hypothetical 1000 tables and how they relate to the general multiplication rule. So we're going to specifically attack questions 17, 19, and 21. So this context has to do with a penalty kick in soccer where it's just the shooter and the goalie. And it's very difficult to stop because the shooter could shoot at any part of the goal and there's no defense, and the goalie has to try to make a save and usually anticipates it. What it says here is cheats to one side. So they jump to one side anticipating it, and maybe they make it, maybe they don't. It's kind of a guessing game. Okay? So the first part here asks us to provide the information using probability notation. So what is the information that's provided? Well, first off, it says the goalie cheats to the right 60% of the time. So the way we're going to write that is just for part A here, probability of cheats to the right equals 60% of the time, or 0.6. Okay? And then the other information we have, when the goalie cheats to the right, so that's kind of like a conditional probability. That's a crummy straight line. So we can take one more shot at that straight line. There we go. So assuming this happens, or given that this happens, the players make about 50% of the shots. Okay, so that would be a conditional probability. That would be something like this. They're going to score or make the shot given that the goalie cheats right. Okay, and that's going to happen 50% of the time. Doesn't matter if you write 0.5 or if you write 50%. And finally, the other bit of information is they make about 70% of the shots when the goalie cheats to the left. So given that the goalie cheats to the left, they're going to make about 70% of the shots. So again, that's P. They're going to score or make the shot given that the goalie cheats left. That's going to occur 0.7% of the time, or 0.7, 70%. Okay, now in terms of creating a tree diagram, okay, extend this a little bit, give yourself a little more space to work this up. Okay, so in terms of creating a tree diagram, it's going to look something like this. Let me grab a new color. Let's go with some green. Okay, so we're going to first split off. We've got the two events, and the possibilities are cheat right or cheat left. Now, if you aren't sure, should the cheating left or right go first, or should the make or miss go first, here's an easy way to think about it. Which happens first chronologically? I mean, does the shot go in and then the goalie cheats left or right? No, that doesn't make any sense. The goalie cheats left or right, and then the shot either goes in or not. So in terms of setting up a tree diagram, it's going to look something like this. Cheat left and right, and then we have to put in the relevant probabilities. So we know that cheats to the right, 0.6, and that's all we're told, but that's all we need, right? Because there's only two possibilities, cheat left, cheat right. Okay, I guess you could say the goalie stays in the middle, but you know, we're assuming that up above it says, you know, the goalie typically cheats to one side, meaning they jump to one side or the other, did not stay. Okay, so we're going to make that assumption that's just two possible outcomes. Okay, based on that, we can branch off the cheat right and cheat left. There's two possible outcomes from there. There's the score or no score. Either it goes in, you know, the make or not make or save. You know, you can think of whatever you want. Makes the shot, does not make the shot. Okay, those are possible outcomes for each of the shots. Now, based on that, we have to look up above. When we cheat right, the probability of scoring is 0.5. Okay, so that's 0.5. I always like to put a 0 in front of the 0.5. And down here, it's 0.5 as well, because 1 minus 0.5 is 0.5. Then for cheating left, it says it's 0.7. So we're going to have something like this. They score 0.7, and the complement of that, 1 minus 0.7 is 0.3. So that's the other possibility. All right, now that I've got the tree diagram set up, I can calculate all these total probabilities over here on the right side. So these are AND situations. Cheats right and scores 0.6 times 0.5. In other words, I multiply the two probabilities. So 0.6 times 0.5, 0.3. Okay? Or 30%. Again, 0.6 times 0.5, 0.3 here. Here it's 0.4 times 0.7. That'd be 0.28. And then 0.4 times 0.3, that would be 0.12. Now these all have to add up to 100% or one whole. So that would be 0.6. Those add up to 0.4. It looks like it works out. Okay? Let me shrink all that down. Just kind of group that and shrink it and move it over because I'm going to create here part B extended here. I'm going to make what's called a hypothetical 1000 table. Okay, that's this piece right here. I'm going to draw right in here. So I'd like to create a 4x4 table. I need it to be a little smaller so it'll fit the space I have. Great, that'll fit right in there. That'll work. Okay, so in our hypothetical 1000 table, you're going to create a 2x2 table. Okay, so we call it a two-way table, but it's 4x4. Okay, and so we'll put in our categorical variables here. So I'm going to put in something like cheats left, cheats right, and then total. And then here, scores or not scores. I'll say it differently. Doesn't score, I guess I'll say. I guess I said no score before. I'll just say no score. It's easy. And then total. All right, so how are we going to take this information? You might be saying, why am I going to make this hypothetical 1000 table? Well, here's the idea. Instead of thinking in terms of probabilities, let's think in terms of concrete so we're going to put some actual counts in here. So we're going to assume we have 1000. You could do it with any power of 10 here. It could be 100, could be 1000, could be 10,000. Typically, we use 1000, just nice round number. We're trying to avoid decimals in here, okay? So assuming that there were 1000 shots, okay? So I'm going to assume 1000 shots here total. So each of these are counts, okay? So the probability of any given shot that the person cheats right is 60%. So that would mean out of 1,000 shots, we would see 600 shots where they cheat right. So therefore, how many does that leave for cheat left? That'd be 400, right? Okay. Now, next, the probability that they score, given that they cheat right, is 50%. So within this column, assuming that they're cheating right, given that they're cheating right, the probability that they score is 50% of the 600. Okay? So I'm going to take half of the 600, which would be 300. And of course, this has to be 300 also. See what we did there? Now, the probability that they score, given that they cheat left, is 70% or 0.7. So I'm going to take 70% of this 400. Okay, so 70% or 0.7 times 400 is 280. That goes here. And then whatever's left, 120, fits here. Now you can fill in your totals over on the right. We've got 580, and we've got 420. And everything needs to add up. So it adds up to 1,000, adds up to 1,000. Okay? You might say, well, what was the point? It's just another way of representing this information. Sometimes it makes it easier to answer a given question having to do with conditional probability. So let's finally jump into part C here, where it says, what's the probability that on the first shot, the goalie cheats to the right and the team scores a goal? Okay, we can look at it two ways. Looking at our tree diagram, cheats right, and scores the goal, there's our answer right here. Okay? So that probability would be 0.3. If we're looking in our two-way table, cheats right and scores the goal, well, that would be right here, 300 out of 1,000, which is the same as 0.3. Okay? Now, we're considering this 19 here. Okay? It says, what's the probability that the team scores a goal on the first shot? Well, two ways to think about it. If we have our two-way table, I'm going to probably grab all this information, just put it to the next page here. Let's grab all that, with the exception of those little bits and this bit. Let's grab all that, put it on the next page for our reference. Cool. All right, so nice. So the probability that a team scores a goal on the first shot. Well, if we're using the tree diagram, we need to consider both places they score. They scored here and they scored here. So for part A, we would be adding up 0.3 plus 0.28. Or 58%. Okay, if we're using our tree diagram, scores on the first shot, well, I just have to look at all the places where they score. So 580 out of 1,000, that's going to work out to the same thing, right? 580 out of 1,000. So they both are kind of handy once you kind of see how they relate to each other. Part B. This is a given that question. Okay, so given that the team scores a goal, what's the probability that the goalie cheated to the right? This is one of those where I find the hypothetical 1,000 table to make it much easier. Okay? Given that the goal is scored, okay, so I know I'm just looking in this top row, what's the probability the goalie cheated to the right? Well, it's going to be 300 out of 580. I think I have that computed here. That's going to be 0.517. Okay? However, if I want to use the tree diagram, what I need to consider is this. Okay, given that the team scores a goal, so I'm going to look at these two areas, this one and this one. This is all the places where they scored. What's the probability the goalie cheated to the right? Well, that would be the top one. Okay, so that's the numerator and the two circled parts, the denominator. So you could do it this way. 0.3 divided by 0.3 plus 0.28. I know that's hard for some of us to wrap our heads around, but one more time it's this. Given that they scored a goal, so I'm looking at the two places they score, and within there, what's the probability that they cheated to the right? Well, that would be the top one. So it's this divided by the total. And I think if you do the math here, it's going to work out to be exactly the same thing as that. Okay, the last question that's relevant here has to do with independence. So if we go back up to this right here, this information we initially got here, just grab this little bit of these facts. Okay? Think about what it means to be independent. If they're independent, the probability of making a shot shouldn't matter whether they cheat to the right or not, right? But look here. They score more when they cheat, they score more when they cheat to the left than they cheat to the right. So because these events, probability, okay, so we'd say something like this. Because the probability that they score when they cheat to the left is not equal to the probability that they score when they cheat to the right, the events are not independent. Okay? If these were independent events, it should not matter whether the goalie cheats the left or cheats the right. The scoring probability should be the same. Thanks for watching.